Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University. Today we are going to talk on module Statistical Mechanics and Introduction from the paper Statistical Mechanics. So students, let us see what we are going to learn in this module. To know the broad learning goals of the course of Statistical Mechanics, to know the overall place of studying statistical mechanics in the study of physics, to give an overview of representative models of statistical mechanics and their applications in various areas of physics, to know the importance of learning statistical methodology beyond physics in the new and emerging areas in biology, economics, geology, ecology, and financial markets. Syllabus covered for this module is answering two questions. What is statistical mechanics and why study statistical mechanics? Scope of this e-course in statistical mechanics is limited to the equilibrium statistical mechanics. What is statistical mechanics? That is what we will look at first of all. Statistical mechanics is basically microscopic route to thermodynamics. It is an effort to understand the microscopic origin of phenomenological theory of macroscopic natural phenomenon called thermodynamics, which has very well established laws based on experimental facts and successful technological applications. These well-known laws are zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, third law of thermodynamics. Interestingly, these laws were known to us much before the revelation of the fact that matter is made up of atoms or molecules and the development of quantum mechanics. As it became clear that macroscopic bodies are made up of such microscopic particles, atoms, molecules, electrons, etc., it was natural to ask the question, can we explain the behavior of these bodies which are typically made up of particles of the order of Avogadro's number, that is of the order of 10 raised to the power 23, starting from the laws governing motion of the microscopic constituents. Let us look at what is the complexity of the task involved. The moment one recognizes that a typical macroscopic body, say 18 grams of water, is made up of 6.023 into 10 raised to the power 23 molecules of water, the problem indeed becomes very complex. Desiring to keep track of all these molecules, their positions and velocities with time by setting up as many equations of motion and solving these is an impossible task by the fastest of the supercomputers available today in a typical lifetime of a person. It is worth estimating this amount of time required for such an effort by a present-day computer. Lack of means to gather such a huge information leaves us with an information crunch also. It is therefore natural to believe that it is a hopeless task which inherently has to begin with perhaps too meager information to arrive at worthwhile conclusions for an enormously complex system. Complexity indeed is an inherent character of nature. It will be worth quoting Nobel laureate Professor P.W. Anderson from his famous article entitled More is Difference, where he sums up the complexity encountered in nature, beautifully underlining its importance in many-body theory and other systems. There may well be no useful parallel to be drawn between the way in which complexity appears in the simplest cases of many-body theory and chemistry and the way it appears in the truly complex cultural and biological ones, except perhaps to say that, in general, the relationship between the system and its parts is intellectually a one-way street. Synthesis is expected to be all but impossible. Analysis, on the other hand, may be not only possible, but fruitful in all kinds of ways. Is there a way out? Yes, indeed. Statistical approach is the way out, because statistical approach offers a methodology to look at such a complex many-body problem to make sense of its dynamical behavior, bypassing the need to solve equation of motion, that is, Newton's equation of motion for a classical particle or Schrödinger's equation of motion for a quantum particle, for each of the constituting particles. As is characteristic of the statistical approach, it may not provide us knowledge of the behavior of each individual particle, yet it is capable of providing average behavior of important physical quantities of interest in a physical system with certain rules of transaction on energy, number of particles, and external conditions, etc. Therefore, statistical mechanics is a way to bring in new concepts besides fundamental laws of classical or quantum mechanics, as the case may be. These new concepts involve probability theory via principle of equal a priori probability and are powerful enough to deal with the complexity of the many-body problems encountered in nature despite lack of information. The basic question which statistical mechanics tries to address is that, can observed properties of a system be obtained from the average behavior of its constituents when these are brought together? Answer indeed leads us to an understanding of macroscopic behavior of a system from microscopic behavior of the constituent particles. What are dilemmas of this approach? To begin with, there are two dilemmas in which one finds oneself when asked to apply this approach. Firstly, with one's training most of the time in deterministic thinking involved in the study of classical mechanics, electrodynamics, theory of relativity, etc., it is not easy to comprehend the reasons to choose the statistical path. Secondly, by looking at a macroscopic body, it is not obvious that what is being observed is an average behavior which stays constant over long periods of time during equilibrium without much concern with regard to the individual dynamical state of individual particles. The prerequisites for this course at BSc level, so that you may appreciate this complete e-course in statistical mechanics, are a feeling for thermodynamics and equation of state, a working knowledge of introductory quantum mechanics and classical mechanics, an intuitive knowledge of the following model systems. For example, classical ideal gas and kinetic theory of gases, harmonic oscillator, free electron gas or what we call Fermi gas, photon gas or what we call Bose gas, examples of phase transitions, and exposure to usage of spreadsheets and running of Java applets of e-resources available on the internet. The broad learning goals of this course are to learn physical concepts and relevant methodology to understand a macroscopic physical system made up of a large number of entities of the order of 10 to the power 23 with a much less information otherwise required for complete mechanical description of the system. To seek a statistical mechanical foundation to the subject of thermodynamics, whose edifice is historically built on the foundation of a phenomenological theory based on empirical facts, to understand a few selected applications of statistical mechanics, to see how postulates of statistical mechanics work to explain a variety of physical phenomena in different areas of physics, to have a holistic view of macroscopic world of physics and beyond from the window of statistical mechanics, and to put in perspective the spread and sweep of the applications of statistical mechanics. So, it's a natural question to ask, what connects thermodynamics and statistical mechanics? That is there a bridge between thermodynamics and statistical mechanics? Answer is yes. Entropy is such a bridge. We would like to know, what is entropy? Entropy of a macroscopic system, which was defined by Rudolf Clausius in a paper published in the Annalen der Physik und Chemie in 1850, is an important measurable physical quantity which offers a bridge to link statistical mechanics, that is theory, with thermodynamics, that is experiment. It will be interesting to understand the meaning of entropy. The meaning of entropy has been a matter of much discussion in thermodynamics in particular and physics in general. Let us look at this picture. It has two parts. The left part is titled order and the right part is titled disorder. Would you like to ask yourself a question? Which is more probable with bricks being unloaded from a truck? And you will naturally come with the answer which is on the right side of the picture. Let us try to understand the meaning of entropy. Say first qualitatively. Physicist Freeman Dyson gave a very interesting explanation of this. And this is the most and the best intuitive interpretation which answers the question, what is heat? He described heat of a macroscopic system as nothing but its disordered energy. He said that its full knowledge requires two numbers. One is a measure of its quantity in, say, joules, and the second is a measure of its disorderliness called entropy. Let us now try to have a feeling of the meaning of entropy quantitatively. The quantification of entropy happened in thermodynamics through the third law of thermodynamics, which is given in this equation. ds is equal to delta Q by T, where S is the entropy, Q is the heat, and T is the temperature. In statistical mechanics, meaning of entropy was given by the famous physicist Ludwig Boltzmann through what is now called Boltzmann formula. S is equal to Kb log of W, where Kb is Boltzmann constant and W is thermodynamical probability. So we are looking at statistical mechanics and then we want to see how it gets linked with thermodynamics. To put it very briefly, statistical mechanics deals with finding essentially the thermodynamical probability by statistical approach, providing a link with other thermodynamical variables via free energy F. In thermodynamics, free energy is a quantity which can be known by measurements alone, whereas statistical mechanics provides a mean to calculate free energy F via Boltzmann formula linking theory with experiments. There is only one way to overcome these dilemmas, and that comes from the success of this approach in explaining various natural phenomena encountered in macroscopic world through the window of microscopic constituents. And this is exactly what we shall explore while going through this course on statistical mechanics. To know about the reach of the statistical mechanics in physics, we must appreciate this fact that in physics, statistical mechanics has been applied to model understanding of many phenomena or laws. The table which you are looking at now provides a bird's eye view of application of statistical mechanics in physics. In this course, we shall study some of these models and their applications. Let's have a look at this table. The model which was proposed for understanding an ideal gas, first of all, was kinetic theory of gases. And it applies to get gas laws and law of equipartition of energy. Then if we bring in interaction, that is, if we try to look at interacting classical gas, the model proposed was cluster expansion model, and we could see its application to derive that famous van der Waals equation. In the case of photon gas as a model, we found it applied itself to explain blackbody radiation spectrum and cosmic radiation background. When we look at simple metals as electron gas and apply Fermi-Dirac statistics, we are able to understand the behavior of metals and go beyond in understanding the behavior of semiconductors and insulators, polyparamagnetism, Landau diamagnetism, and quantum Hall effect. In the case of Bose gas and Bose-Einstein statistics, we found we were able to apply it to understand specific heat of solids and Bose-Einstein condensation. Ising model and lattice-gate model were applied to understand ferromagnetism, antiferromagnetism, binary alloys, phase transitions, lattice model of fluids, adsorption surfaces, DNA melting, etc. In the case of interacting Bose system model, we could appreciate and understand the phenomenon of superfluidity and superconductivity. When it comes to dense electron gas, we were able to explain the behavior of white dwarf stars in astrophysics. The theory of Brownian motion via random walk over a lattice helps us to understand phase transitions. Self-avoiding random walks help us to understand polymers, and we are led to dynamical equations to understand diffusion via diffusion equations. Heisenberg model finds itself explaining ferromagnetism and antiferromagnetism. Landau's theory was used to explain continuous phase transitions and phenomena near critical point. Renormalization group methods were used to apply and understand critical phenomenon. Monte Carlo methods help us to understand modeling of fluids, polymer systems like proteins and membranes, etc. Molecular dynamics offers us a way to understand liquids, chemical physics, material science, and biomolecules. It will be worth appreciating right at the beginning of this course how this statistical mechanics methodology goes beyond physics. Indeed, statistical mechanics goes much beyond its usual link with thermodynamics. The methodology of statistical mechanics has become a very important tool in the hands of scientists who truly study very complex systems like biologists, chemists, geologists, information scientists, computer scientists, ecologists, social scientists, and economists, etc. For all these disciplines, use of statistical mechanics has been possible by drawing very interesting analogies between corresponding variables. For example, in economics, a system of particles becomes a system of agents. Energy E, which is a conserved quantity, becomes money M, and temperature T becomes effective temperature of the system measured in money currency, that is dollars, following Gibbs distribution law with similar rules for trading. In the case of ecology, where ecologists are interested in collective behavior of populations consisting of constituent particles, for example insects, in the form of biological organisms, principles of statistical mechanics can be usefully applied. Biologists are applying tools of statistical mechanics to a host of problems like force extension curves for DNA, lattice models of protein folding, analysis of polymerization and molecular motors. In information theory, one deals with networks, to be precise, communication networks, dealing with, say, people talking on phones or investors in financial markets, etc., exchanging information with one another in a very complex manner. Shannon was the first person to define information quantitatively analogous to entropy. Insurance companies, financial markets, psephologists, people who predict the results of polls, bioinformatic experts, traffic model experts all make use of tools of statistical mechanics and find training in the ideas of statistical mechanics a fundamental requirement to deal with the complexity in these systems. This has enriched their own field and the field of statistical mechanics. So, let us ask ourselves, why study statistical mechanics? In fact, the success of statistical mechanics lies not only in understanding physical phenomenon, but goes much beyond that. It has influenced many areas beyond physics across disciplines in science, engineering, mathematics, and social sciences. It has a very wide reach and a rich variety of models or methods which are applicable in analogous situations. So, students, let us now summarize what we have learnt in this module. We have learnt about broad learning goals of this e-course in statistical mechanics and what are the prerequisites for appreciating it. That despite the laws governing the constituent particles are well known, yet coming together of a large number of particles makes the understanding of such a system possible only by statistical means, revealing new laws unheard of in the realm of individual particle behavior. That new laws are probabilistic in nature and give an average behavior of the properties of the system. That how statistical approach relates to thermodynamical physical quantities via Boltzmann's famous relation for entropy, and thus opens a pathway to link statistical mechanics with thermodynamics, a very well established phenomenological theory. That statistical mechanics deals with a many particle system with a challenge of handling complexity of them all together, usually with a very meager information available at any point of time. That the long list of its applications provide a wide sweep and utility of statistical mechanics, not only in understanding physical phenomena, but also phenomenon encountered in variety of diverse fields in biology, economics, ecology, information theory, and computer science. Thank you.